Okay, welcome everyone to today's INQA seminar on the 3rd of June 2025. Gives me great pleasure to introduce today's speaker, who is Joey Tindall from the Flatiron Institute. And Joey will be talking to us today about quantum simulation with higher dimensional tensor networks. So over to you, Joey.
Great. Yeah, thank you very much for inviting me to speak today. I'm a associate research scientist at the Center for Computational Quantum Physics, which is part of the Flatiron Institute, research institute in New York, funded by the Simons Foundation. And my work at the Flatiron Institute is focused on using higher dimensional tensor networks, so two three-dimensional tensor networks, to do effective quantum simulation with classical resources, so classical computers. And it's a very exciting time at the moment, I think, for quantum simulation, because there's such a wide range of devices that are becoming increasingly capable of simulating very complex quantum systems. And the range of these devices means that the range of systems available, whether it's sort of like simulating quenches of transistor icing models or quantum materials or fermionic or bosonic systems, there's such a wide range, and these experiments are becoming increasingly complicated. But from a classical point of view, quantum simulation is very difficult, right? So simulating quantum dynamics of, say, a many-body system, generically, you have your entanglement kind of grows linearly in time when you quench a quantum system out of equilibrium. And then that gets combined with the fact that like various numerical approaches to simulating quantum dynamics come across a lot of stumbling blocks that aren't necessarily present in equilibrium. So for the time-dependent variational Monte Carlo methods, say methods which are based on some ansatz like a neural quantum state, for capturing the time-dependent wave function, you need to kind of do an inversion or a pseudo-inversion of the quantum geometric tensor every time step. And this raises a lot of numerical stability issues that aren't present in equilibrium simulations. Meanwhile, matrix product state-based approaches, which sort of try to capture the time-dependent wave function as an ansatz based on a connected series of low-rank tensors, suffer from the difficulty that the entanglement grows very large, so their bond dimensions and the sort of resources that you need grows very large, but also that the kind of most popular ansatz and the most favored ansatz is the one-dimensional ansatz, but these quantum devices are capable of simulating quantum dynamics in sort of 2- and 3-dimensional lattices. And these kind of systems are not well captured by a matrix product state ansatz. So it's sort of like there's a lot of rapid movement going on in sort of quantum technologies and the systems that they're capable of simulating, but the classical methods do have a lot of stumbling blocks. And as a result, there's been a lot of work recently from these experimental devices, essentially making claims of quantum advantage, that they can simulate some quantum dynamics or some quantum circuit that you can't with classical methods, whether that's some kind of random circuit or the quench of an icing model, or in a very recent case from DWave, the sort of disordered quantum annealing, a quasi-adiabatic annealing process in various disordered quantum lattices. And these numerical difficulties that I talked about and the kind of growing complexity of these devices are exactly why these papers are coming out, because they're sort of capitalizing on the fact that this is a very difficult thing to do, and these devices are becoming increasingly powerful. But obviously, there are a huge range of possible ways that you could simulate a quantum system, and it's pretty hard to do an exhaustive comparison of classical methods in this domain. So our approach to quantum simulation is based on this kind of what I call a structured tensor network approach, where you have some quantum system that has some underlying lattice structure. Maybe you're kind of thinking about an icing model on a certain lattice or a bosonic model on a certain lattice, and then to use as an ansatz for the many-body wave function a tensor network that really captures that time-dependent wave function and actually encodes the underlying lattice structure. So unlike the matrix product state approach, it's a sort of an adaptable tensor network in some sense that you choose based on the kind of structure of the problem at hand. And so I'm going to talk about the kind of success we've had in adopting this approach and how this kind of actually really pushes the boundary of classical simulation, is allowing us to, keep up or, supersede some of the results coming out of these quantum devices. So, a bit of a primer, what is a tensor network? So, a tensor network can really just be seen as a compressed format for a high dimensional data structure. So you have some very high dimensional array, which in kind of the quantum world might typically be the coefficients of the many-body wave function, where each of these dangling legs represents a different dimension, like a different spin in the system. And obviously this, the size of this array goes exponentially in the number of dimensions you have, the number of qubits. So if you're going to kind of simulate a quantum system with more than 30 qubits, you need to compress this object somehow. And a tensor network is a compression of this object into a series of low-rank tensors, typically one for each of these qubits, with these kind of virtual indices which mediate correlations between the qubits. And so the goal of kind of working with tensor networks is to find sort of very effective tensor networks that can actually compress this structure and kind of take you away from this exponential scaling to something that is potentially polynomial in scaling, so that these virtual indices don't scale with the size of the system. And as I said, the kind of go-to tensor network ansatz is the one-dimensional tensor network ansatz known as the matrix product state, which has been incredibly successful in the last decades in studying sort of quantum systems, especially in one dimension. And they have a lot of nice favorable properties that make them, has made it so successful. So you can efficiently kind of query these matrix product states and extract things like observables or the total square norm of the matrix product state in time that's polynomial in the network parameters. You can prove for certain problems, say the ground states of one-dimensional quantum systems, that this is actually an efficient ansatz. And if you're away from criticality, then you really can represent the state of the system with polynomial resources, not exponential resources. And I think a big one that is sort of maybe overlooked in some senses is that it's much easier from a kind of software perspective and an algorithms perspective to construct code that works with a one-dimensional matrix product state, which has sort of contiguously indexed tensors, where each tensor is really just like a list of matrices. This is much easier than working with a general kind of tensor network ansatz. And this kind of combined with the history and the properties has led to a lot of stable, well-designed code bases and algorithms for working with this object that don't really exist for the more general tensor networks. And, part of my work is to really actually try to create code and algorithms that lets you work with these objects and lets you attempt to do quantum simulation with these objects. And, that's not to say that people haven't worked on sort of two-dimensional tensor networks like projected entangled pair states and haven't, done a lot of successful simulation with these. But the 2D square lattice is actually one of the hardest tensor networks to work with. It has a very large tree width, which means you can't generally contract it efficiently. And there are a lot of algorithms and software libraries that are kind of a bit rigid. They sort of focus, say, specifically on the square lattice tensor network. They focus on contracting this network as precisely as possible at the expense of kind of being able to capture like virtual correlations that are particularly large. So there's a lot of limitations in literature with working with an ansatz like this compared to the matrix product state, some of which is sort of just a result of the ansatz being more complicated, but other parts, such as needing to contract it precisely, are not necessarily a sort of constraints that maybe might be overimposed. And so we take the more kind of general view of thinking about these objects more generically, contracting them more approximately and seeing where we can get when we do that. So this is what we're kind of like graph-based approach to tensor networks, where we really just view a tensor network as a graph. On the vertices live tensors or collections of tensors, and the edges describe which tensors kind of share mutual indices. And a very kind of simple but powerful tool that we use to work with these objects is belief propagation, which is a very well-established algorithm for performing statistical inference on probability distributions, but now is coming to the fore a bit in the tensor network community because it could be repurposed to contract and work with tensor networks. So, if you have a tensor network, like I kind of write down here, where again, these individual vertices might represent a single or a collection of tensors, then belief propagation works by just defining message tensors that live in both directions on each edge of the network and having a simple self-consistent update rule for how to pass messages around the network. And you can kind of efficiently iterate these update equations until they converge. And then these message tensors are very useful because they can be used to infer a lot of properties from your tensor network. So for example, the contraction of the whole network, which here will just yield some scalar, can be approximated based on sort of local products of message tensors incoming to the given vertex that they kind of point in the direction of divided by some normalization factor. And this is a very useful thing because you can very efficiently compute this approximate contraction of the network in comparison to a general loopy network where typically you can't do an efficient contraction of the whole thing. So this gives you a rough but very quick thing to compute. It's independent of the tensor network. You can do it to any kind of tensor network of any structure. And importantly, it's exact on a tree tensor network. So if there are no loops in your tensor network, this is an exact formula, and you recover kind of well-known ways to contract tree tensor networks. But if there are loops, you typically have some sort of error that decays exponentially in the smallest loop size. So you kind of have an understanding of exactly, how bad your approximation is, your belief propagation approximation is. And we've shown that essentially with these belief propagation tools, you can do a lot of simple things with tensor networks, like take measurements. If it's a tensor network representing a quantum state, measure some kind of local observable, apply a gate, like a gate that might be part of some quantum circuit. You can kind of apply a gate to the tensor network in the presence of these message tensors. You can gauge a tensor network so it has favorable properties, and we kind of unified a lot of existing, tensor network ideas in the belief propagation language, which almost is like the simplest thing you can do on a tensor network. And this has been extremely effective because several years ago, IBM had a notable paper in Nature in which they simulated the discrete time dynamics of an icing model on their Eagle processor. So there's this kind of 127 qubit heavy hexagonal processor here. And they claim that the dynamics of this system, which their quantum processor was able to, approximately get good, accurate results on, was well beyond the reach of classical methods like matrix product state or expensive projected entangled pair state methods. And you can kind of see that here because this is kind of a regime of the dynamics, which the exact solution is known, and this dotted line here is the exact solution. These white circles that kind of follow that line are the IBM process, but then this kind of red and these orange curves are matrix product state methods or expensive PEPS method. But we actually showed that you can see these crosses here, that just using belief propagation to apply gates, measure observables, we can in minutes, on a laptop, get almost machine precision accuracy for the dynamics of the system by just using a more approximate 2D tensor network approach that captures the geometry of the system. And then even when you go out to much deeper circuits where there's sort of no known solution, we're able to extrapolate our results to infinite bond dimension and essentially get a very accurate answer to the dynamics of the problem, more accurate than the quantum processor or these benchmark methods. And this kind of really showed to us the power of using, an approximate contraction scheme, but one that allows us to keep up with the entanglement in a quantum process and really simulate the dynamics of a big 2D quantum system. But one of the kind of questions that we had after this is if we had kind of more complex lattice structures, lattices which have smaller loops where we know belief propagation can fail, what do we do? You know, how can we correct for this, and actually do simulations on these more complex lattices? And there's several ways to do this, and I won't kind of go too far into the technical details, but you can kind of correct belief propagation in several ways. One is you can kind of give your matrix, your message tensors extra virtual indices, which connect to each other, and sort of carry correlations. And you can, if you can keep yourself within the place where you still have a self-consistent update rule, then you can essentially do these correlations, sort of correct belief propagation. And this is kind of like, you can show the well-known kind of boundary matrix product state approach to contract a 2D tensor network is within this kind of formalism. So you can contract two-dimensional tensor networks by kind of like bringing matrix product states in from the boundary and slowly contracting them inwards, making some approximations. And this is sort of like running belief propagation, but instead of having little message tensors, you have matrix product states, which are your messages and get passed between the columns and the rows of the network. Another kind of more recent approach is this loop correction approach by Glenn Evenbly and others, in which essentially you kind of have your belief propagation messages that you converged, and then you form these anti-projectors to sort of the anti-projected belief propagation subspace, and you can kind of insert them into the edges of your network and kind of count up, write the contraction of the network as some massive multi-configurational sum involving projectors and anti-projectors on the edges of the network. And then you can kind of truncate this sum and only account for some number of anti-projectors that keeps the contractions efficient. And basically you can kind of view belief propagation as the 0th order term in this sum. And then, you can first order term in this sum is basically contractions involving the smallest loops of the lattice with little BP messages coming onto the boundaries. So this is a relatively new method about how to kind of correct away from the BP point in tensor network contractions. And we kind of had an opportunity to kind of put these belief propagation and then their extension tools into practice with a recent paper from DWave studying annealing processes on sort of disordered transverse field Ising models. So essentially, the experiment involved kind of studying a range of different lattices, so a square kind of cylindrical lattice structure, cubic lattice, a diamond lattice, and then a kind of infinite dimensional biclete lattice. And essentially the kind of ground state of this Hamiltonian in terms of the transverse field part, so sort of a state which is polarized in X, was essentially simulated. So a quench of this system was simulated with these parameters slowly varying in time. So a kind of standard quantum annealing process. And then at the end of this quench, the 2-point ZZ correlations in the system were measured across all pairs of lattice sites. And then for small systems where matrix product states can actually be used to generate essentially a ground truth, the resulting correlations were compared to their exact values in this error metric, which I write here, which is sort of an average over all the different 2-point correlations compared to their exact values, was kind of measured and compared for both the DWave, Advantage 2 processor, and then classical methods such as matrix product states, projected entangled pair states, and neuroquantum states. And essentially, DWave's results show that, for example, on cylindrical lattices, if you compare the accuracy of the quantum processing unit for a quench of, say, an 8x8 cylinder, that for short time quenches, projected entangled pair states, so cylindrical tensor networks are able to reach accuracies that are below that of the annealer. But then as you get to very long quenches, where a lot of kind of spin glass correlations build up in the system, these projected entangled pair states appear to become more limited. And even as you increase their bond dimension, they don't seem to be able to achieve errors below that of the annealer. In fact, they kind of seem to be saturating. And then if you kind of look at how a matrix product state ansatz performs, you see that, the complexity of the simulation for a fixed accuracy goes exponentially on all of these lattices. in the system size. And this is, as I said earlier, because the matrix product state is such an ansatz that really just isn't suited to simulating large 2- and 3-dimensional systems. It cannot capture even like relatively low entangled 2- and 3-dimensional systems. And then for the more general 3D lattices, there are various arguments about how sort of if you were to do some kind of like, full, some various different gate applications to 3D tensor networks, this would result in sort of scalings with bond dimension on the order of bond dimension to the 30 or bond dimension to the 12, and therefore these were just not it's not possible to do classical simulation with a 3D tensor network in this regime. But we kind of took up this challenge with our belief propagation methods and those kind of corrected variants I mentioned of trying to simulate these systems and seeing how well our codes could do. So, we took our structured tensor network approach to the problem, and we focused on the 2- and the 3-dimensional lattices, which are sparse lattices. So they have can have an efficient tensor network representation in the large system size limit. And we tried our kind of method of basically applying gates of the system, so running the time dynamics with just simple belief propagation, and then measuring these 2-point correlations with things like loop corrections and boundary NPS, because we know that belief propagation, as was shown in the DWave paper, is not going to be enough to get accurate results for the system. So, we did some various kind of clever tricks that sort of like, I think, pushed existing algorithms a bit. For new ways to contract tensor networks and do some kind of clever things. So for example, in the cylindrical case, we have our cylindrical tensor network that represents the time-dependent state of the system. And then at the end of the quench, and we want to measure a ZZ correlation, we kind of do this thing where we insert one of the Z correlators into the tensor network, and then we run belief propagation around the circumference of the cylinder, passing matrix product state messages around it until they converge. This is sort of like a hybrid of the belief propagation and boundary NPS approaches to a cylindrical network. And then once these converge, you can pull out basically sigma Z on the site that was originally the operator was placed on, and any other site you want, from those converged messages, which means you can basically get all 2-point ZZ correlators completely non-local in essentially time that scales with the square of the number of qubits. So it's like an efficient way to measure all of those correlators, even non-local ones, which, generally non-local measurements with 2D tensor networks is not something that's really been done much before, because it's not obvious how to do it, but this kind of gave us a way to do it. So in this case of the cylindrical lattice, we get kind of actually drastically, but notably improved results compared to the cylindrical results from the DWave paper using our kind of new contraction method. In the kind of low quench times, we get very accurate results, kind of down to errors well below 10 to the -2, sort of an order of magnitude improvement on the processor, and sometimes on the PEPS method used in the DWave paper. And then even at the longest quench, which is much more difficult and there's a lot more kind of correlations to capture, we are able to kind of see an improvement with increasing bond dimension, and kind of we don't quite see this saturation that was seen in the DWave paper. And then kind of what's really cool is that if we kind of look at the error we get in the cylindrical system as a function of its system size, specifically its circumference, we actually see that our errors are decreasing exponentially with the size of the system for a fixed bond dimension. And this is because of the way that we are passing these matrix product states around the circumference of the cylinder. And so it's like we're running belief propagation on a system with a single loop of size L. And as I said earlier, generically, the error from belief propagation will go exponentially down in the size of that loop. And that's exactly what you see here. These pink dots and this dotted line is kind of showing that happen, which means that our method sort of for a fixed accuracy kind of will improves as you increase the system size. So it gets lower accuracies as you increase the system size, but with a wall time that, to run the time evolution is only linear in the number of qubits, and to get all the 2-point correlators is only quadratic. And there's a quadratic number of 2-point correlators, so you can't do a better scaling than that. Then we also kind of, wanted to try our methods out on the three-dimensional lattices as well, because these are very intriguing to us, and very little results from quantum simulation, especially on the classical side in three-dimensional systems. This is kind of generically considered to be beyond the reach of tensor networks, because 2D lattices are so hard. So the kind of argument is surely 3D lattices even harder for a tensor network. But we kind of, again, you know, in the case of, say, a diamond lattice, we constructed a tensor network that looked like the diamond lattice. And then we measured the 2-point correlations in the system by essentially placing the two ZZ correlators where we wanted them, and then contracting the whole resulting network with loop corrections. And kind of summing up loops up to a certain size that were kind of within the reach of our computational resources. So in the case of the diamond lattice, when we did this, basically, essentially we saw that for kind of the shorter quenches, actually kind of simple belief propagation, so 0th order belief propagation, was enough to get very reasonable errors in the diamond lattice. But then for the longer quenches where more correlations build up, you can see here that the simple belief propagation isn't, you know, I mean, it's not a terrible result, but it, you know, it gets an error above that of the quantum annealer. And actually you kind of need loop corrections. So these kind of darker shades of blue are using increasing orders of loop corrections. So the medium blue is sort of first order, where you have to contract these loops of size 6 in the diamond lattice. And then the darkest blue is where you have to contract up to these kind of double configurations, these genus 1 loops or genus 2 loops. And when we do that, we actually, you know, for an increasing computational cost, but still something that is within reason. And I think these largest loops correspond to contractions on the, I think there might be bond dimension to the power of 7. So we can get errors that are very decent, and seem to be scaling reasonably with system size, at a cost of bond dimension to the power of 7. And this should really be contrasted with the kind of bond dimension to the 12 or the 29 kind of statements from the original DWave paper, that when we take a kind of more belief propagation based approach and correct away from the simplest limit, we can actually do things with relatively reasonable scaling for our classical methods. And, you know, one of the big questions is, of course, how do we go to, you know, how do we verify some level of ground truth in a bigger lattice, right? Like, you know, here we only presenting results up to 54 qubits because that's the only regime in which matrix product states can be used to give a ground truth to the problem. So how can we have any idea if our results are good for larger system sizes? So something we did on the kind of, say, 128 qubit lattice was sort of compare the correlations we get, the ZZ correlations we get for, say, 2 different bond dimensions in our simulations for some fixed, say, first order belief propagation, and see how these kind of collapse. So if we compare bond dimension 2 and 4 to each other, we can see that our simulation is clearly not convergent at all in bond dimension, and you know, the correlations you get are very different to each other. But then as we compare, say, 4 versus 8, we can see actually these kind of correlations are correlating with each other pretty, you know, pretty noticeably. And then by the time we compare, say, 8 to 48, we actually get, you know, incredibly converged correlations with respect to each other. When we kind of fix the loop correction order and compare different bond dimensions. Similarly, if we do the same in kind of loop correction order, so 0 versus first order and then first versus second order, again, we see kind of convergence. So we can actually convince ourselves for diamond lattices, say, involving a couple of hundred qubits, that we can reach errors on the order of 10 to below 10 to the minus 2, which is well below that of what the quantum annealer can achieve. So essentially, actually, you know, in these kind of certain regimes, we can convince ourselves of, you know, some level of convergence in a 3D tensor network simulation, which I think is very exciting. And then, you know, for more, you know, the underlying physics in the system is that you have a quantum system being driven through a phase transition at a finite rate, right, which is controlled by the total annealing time of your quench. And this means that on the other side of the quench, or at least the kind of critical point, the correlation length should scale with the total quench time raised to some power, which is set by the Kibble-Zurek exponent, which kind of sets the universality class of the corresponding quench. And this kind of immediately tells you also that for a finite quench in finite time, the correlation length in a big enough system is essentially finite. So that means there does exist a tensor network that matches the lattice that has a finite bond dimension that must capture the final state of the system. It can't have an infinite bond dimension. So actually you can kind of you can immediately, even if the polynomial scaling is high, show that this, the physics of this on these 2- and 3-dimensional lattices is simulatable in polynomial time with classical resources purely by, by this argument, essentially. And, we can actually see this scaling manifest. So when we look at large cylindrical inputs, we look at how the 2-point correlations decay with distance for 2 different cylinders and for a range of different quench times in different shades of blue. And then when we rescale the distance by this kind of inverse of the annealing time raised to the power of 1 over mu, the Kibble-Zurek exponent, we see the expected collapse. So we essentially see the collapse of the correlation function, and we see the Kibble-Zurek physics emerge, and the values we get for the exponent appear to be consistent with, those of DWave and those of a relatively recent Nature paper, which studied kind of 2+1D Monte Carlo simulations of these disordered 2D Ising systems. And they kind of extracted a value in the thermodynamic limit, which is pretty uncertain, but their finite size results are very consistent with the numbers that we see. So we can really kind of see the Kibble-Zurek physics emerge in our simulations, which is really nice. And kind of to conclude, I think, it's very exciting because I think there's a lot we can do with these quantum circuit simulation tools and codes and these kind of 2- 3-dimensional tensor network approaches. We have a lot of interest in kind of looking into various physics in 3 dimensions or fermionic problems in 2 and 3 dimensions, and kind of continuing to push the algorithms and the code that we're developing. And, I should say thank you to my collaborators here at CCQ and NYU, and also mention that sort of, this code is open source. We have the iTensor Networks package, which is sort of the sandbox for working with all these tensor network methods. And then this kind of wrapper, I have like a forward wrapper for it so that you can do kind of easy quantum circuit simulations with the techniques I've talked about in kind of a user-friendly way. So yeah, thank you very much for listening.
Great, thank you very much, Joey. A lot of interesting things for us to consider there. And I guess I'll open it up for questions. So if anybody has a question for Joey, either speak up or post something in the chat or raise your hand or whatever. Andrew King has literally raised his hand. Andrew, over to you.
I can't see myself, and I can't find the button to raise my hand. Thanks for the nice talk, Joey. I have an endless list of questions, and you've already been very gracious in answering them. So thank you for that. I'm just curious about the MPS method on the cylinder, which I just want to confirm my understanding, because it was a nice explanation that you gave that I didn't really understand initially. But it's mentioned in the paper that it requires a 2D open in 1 dimension, right? And
yes,
is this because it's inconvenient to generalize, or because it's kind of impossible fundamentally?
It's not impossible. It's that you kind of, the key step of the algorithm is that you have this MPS times this MPO, which represents kind of the column of your cylinder, say, and you want to fit it to another matrix product state. Because
so the right way to think about it is really just propagating information from an MPS on one column after another. Okay.
Yeah. And if it's an MPS, you have things like it has an orthogonality center, and you can show that you can do this in like some fixed scaling time. But if it was a ring that you were trying to pass through, basically you'd have to either make another approximation like belief propagation on it, or you would end up with an algorithm that just has a higher cost. So it could be done, but it would just be more costly.
Yeah, I noticed in that Quantinuum paper, they studied torus to make it more difficult for MPS.
Yeah,
I
I
was like,
think that
well,
was
how do you get the ground truth then?
Yeah.
That's why we
Yeah.
did cylinders.
Yeah.
But the other question I had was, you've only studied kind of up to a certain bond dimension, but you do see errors growing steadily in the correlation length, which is exactly what we saw for PEPs. And do you think that it's ultimately going to run into the same limits? Maybe just
That's a
at
good
a larger
question.
correlation length?
You mean like if we did a quench at say 40 nanoseconds or something?
For example.
Yeah, no, that's a good question. I would assume so. We haven't tried it, and it's something that I'm meaning to run some simulations on. Obviously, I guess, yeah. At some point, you should end up in like the right classical solution. But then if the ground state manifold is degenerate enough, then that still means that you should
Well,
have.
yeah, like these are even 8 by 8, these are kind of relatively small inputs. So there's a kind of a competition between annealing so slowly that you become adiabatic versus the Kibble-Zurek picture, which is going to be generalized better to large systems.
Yeah. No, my expectation was it should become harder, and if I put a plot here of 40, that this should be up here somewhere. But it's certainly something I'd like to run. To watch how the entanglement kind of grows in these simulations.
Okay. And final question before I just test everybody's patience too much. So these the loop corrections, they obviously rely on having sufficiently good local information to actually do the corrections using. So in a large limit of bond dimension, are these guaranteed to improve accuracy, or is it just kind of
No, it's more, I would say, like obviously you can show that if you capture all the terms in the sum, it must give you the right answer. But, if you're truncating that sum heavily, it's reliant on the correlation length being finite. And I think most specifically, the correlation length probably like, not extending much beyond the largest loop size that you account for. So it's perfectly possible to construct a pathological PEPs whose sort of, if you look at the loop correction sum, the most dominant term is actually the term at the end or something. So it's very much, reliant on like being in a certain limit, basically.
okay?
I would say. Yeah.
Okay,
But
thanks a
then,
lot.
yeah, thanks.
I see that Alberto Mosera has a question.
Hello, Joey. Thanks for the very nice talk. Maybe I have some similar questions to what Andrew already asked. So I have a curiosity about, is it known this belief propagation PEPs wave function, what kind of states they can capture? Can you conclude that it captures area law states in 2 and 3D? So is that known states that these quantum states that you are working on or you developed can approximate efficiently?
Yeah, so it's sort of like we use belief propagation to like apply the gates, but if you don't make any truncation, you'll apply the gates exactly. So, you can generate like an area law PEPs with this method, and it will exactly capture such a state. Obviously, if you have something that has a volume law, then you're going to need a bond dimension that goes exponentially. And belief propagation won't save you from that, essentially. But what belief propagation does let you do is basically, because it's so cheap, it lets you crank your bond dimension up, say on a 2D square lattice to maybe 50, or on like a diamond lattice to something even on the order of hundreds. Something that if you tried to contract the tensor network exactly, you just couldn't do. So it sort of actually lets you kind of reach much higher entanglement regimes than usual. But it still does have the limitation that at the end of the day, if it's a volume law state, then your bond dimension has to be exponential, and you're going to get an exponential scaling.
And the second question you probably already, thank you. And the second question is, what's the role of the correlation length? So you probably already mentioned this, that you need to,
Yeah, it's sort of like you can kind of see it as like the zero forward belief propagation. If your correlation length kind of is smaller than the smallest loop in the lattice, then zero forward belief propagation is going to give you a very good answer, essentially, because it kind of like the system doesn't really have loop correlation, so it doesn't have significant contributions to, say, the actual observables from things that go around the loop. But then if you do have like a larger correlation length, you essentially need to contract larger loops to account for that. And that's where you need things like loop correlations.
Yeah, because my puzzle is, suppose you go to very large TA, to very large annealing times. Eventually you should have a entanglement entropy that is log 2. That is very small, but the entanglement length, if you want, it's infinite, because that's a trivial state. And so on one end, I think this method should be very good, because in terms of, you need very much smaller bond dimensions, but then the loop correction, they're gonna become an issue at that point.
There's always going to be some like trade-off, and there's going to be some point at which, this becomes much more complicated. And if you go to a long enough quench or create some state that has a long enough correlation length, you could end up in trouble. Basically, you can imagine actually the correlation length, actually this should be a fraction that's like the smallest loop size divided by the correlation length in the system, or maybe the inverse of that. And then it becomes a question, of like, but then there's also the question, how much does that correlation length affect what you're measuring? If you're measuring, say, like a local observable, and in the DWave experiment, these weren't, so this kind of makes things difficult. But if it was a local observable, then you could have a state that has a very large correlation length, but that doesn't actually impart any information on what the value of, say, the local magnetization is. So you may get away, despite the fact that the actual capturing the total wave function is very complicated classically and requires like an exponential bond dimension, you may find that you can get away with using a very small one if you want to extract certain properties from the system.
Okay, thank you.
Good, maybe time for one more question, which I shall hand over to Jack Raymond.
There's anyone not involved with us who wants to ask a question, I can give you. The convergence of correlations with bond dimension is actually not a guarantee of correctness, right? Because you can have, say, a Boltzmann distribution with bond dimension 2. You see convergence in the correlations, but they don't reflect accurately they don't reflect accurately the correlations of a correctly contracted Boltzmann distribution.
So you're saying that the convergence here might not indicate convergence?
Yeah, convergence within there's a systematic error associated to like the locally tree-like method. So for example, a Boltzmann distribution you can represent with bond dimension 2.
Yeah.
And so you see immediate convergence, right? But it doesn't actually indicate correctness. Is that sort of reasonable?
Yeah, I would say it's sort of, I think you're probably right that it doesn't mean I can really guarantee technically that if I went to the next order of bond
I'm
dimension.
convinced, by the way. I think
No, I
think
you're like you could definitely construct states like you said where you could have plots like this and then suddenly it could go wrong. Empirically, I think we're somewhat convinced that this is convergence of the correlations. But I think technically you're right that yes. I mean, it's the same way that like when people do matrix product state simulations and they extrapolate in bond dimension, technically you could go to a larger bond dimension, it could all go wrong, but kind of empirically when people see the convergence they expect,
well, I think but it's different because in MPS you have no locally tree-like approximation. So I think it's correct in the limit of high bond dimension.
I see. But here we also compare, I mean, we're limited on how much we can compare, but we compare like 0th and 1st order BP versus 1st and 2nd order BP. So sort of like we try to also show some convergence in loop corrections as well to like get away from that part.
I get a very quick part 2, right? Everyone else did.
Yes, that's fine. That's fine.
The scaling in 2D, so at the end of the dynamics, you use a boundary contraction method, basically, which is essentially exact for finite correlation length, I think. That's my understanding because the corrections are
if the correlation length doesn't get around the cylinder and then you use a big enough MPS, then it's exact.
But then for 3D and above, you're using loop corrections, and the number of loop corrections has to grow exponentially in the correlation length, right, to be accurate? So it's sort of, you can't capture scaling, I think, if the correlation length scales. Your algorithmic complexity has to scale exponentially, I think.
If your correlation length doubles, then in principle you have to kind of count like loops of double the size.
Yeah,
I mean the number of
loops
does go exponentially in the loop size that you count for. So yes, that's a good point.
I think so. Yeah, so maybe the scaling phenomena will be very difficult to capture in 3D and above, even if you captured it in 2D.
That's a fair point. Yeah, that's a fair point.
Okay,
that
cool.
could well be true. Yeah.
Good. Thank you, everybody, for your questions. And thank you once again to Joey for some very interesting presentation. Thank you. Round of applause from us. And I'll just point out that there is no online INQA seminar next week because that's a clash with AQC in Vancouver. So I look forward to seeing many of you at that conference. And then the next INQA presentation is on the 17th of June, and that will be Kartik Agarwal from Argonne National Lab. So I'll either see you in person in Vancouver next week or online in 2 weeks' time. Thanks to everyone for attending. Thank you, Joey, once more, and I look forward to seeing you soon. Bye-bye.
Thanks.